All right. Um, so what we want to do today, let's get started. We want to talk about well, we last time we talked about using what we know about limits of functions to show that sequences converge. So we want to talk about a couple more tools that we can use to decide if sequences converge. And one of the tools that we're going to talk about, the idea of bounded and monotonic, is really kind of at the base of everything that we talk about. So the first thing is the squeeze theorem. Squeeze theorem is nice when you can use it. The hard part about using the squeeze theorem is you have to know something about inequalities. So things have to be greater than and less than, that kind of thing. So what we're going to say for the squeeze theorem is if we have some sequence that converges. So this limit as n approaches infinity of a sub n is some limit, and that also equals the limit of some other sequence. And we're going to say we have some integer exists such that all the terms of some other sequence are between each term of these two sequences that we know converge to the same limit. So eventually, the terms of this C sequence are between the terms of the A and the B sequence. Then that guarantees us that the limit as n approaches infinity of C sub n equals L also. And the way I think of this visually, well, and the reason we call it squeeze theorem is the limit of the C sequence is squeezed between the limits of the A sequence and the B sequence. So the way I think about this is just, it doesn't have to look this way, but I think of something like this. I think of my A sequence being like this, and I'm going to connect these with a dotted line. Yes?
When you say the smaller n has to be greater than the bigger n, what does that mean?
It means that the terms don't have to be between each of these for every single possible value of the sequence for every term. Just eventually, when you get out a certain number of terms, and after that term, all of the C terms of the C sequence are between the two, then you're good. It doesn't have to be for every single one, but just eventually. Yeah.
Is it also called some kind of sandwich theorem?
Sandwich theorem, yeah.
Oh, hey.
Yeah. So these are my A sub n's in blue. This is how I think of it. And I'm going to just, they don't have to be negative, but I'm going to put the B sub n's down here like this. So these are my B sub n's, and I'll connect those with a dotted line. And these are both approaching some limit. And I'm going to put the C sub n's, so kind of like this. But then eventually, my C sub n's go in here. So my C's are doing this. And eventually, all the C sub n's, I'll put the next one over here. These are C sub n's. So eventually, all the terms of my C series are in between the A and the B, the terms of the A and B series. They all have to converge to the same limit. And often what's convenient for the squeeze theorem and the sandwich theorem is, use it without thinking about it, is the lower sequence. Did I write that? I wrote that backwards. This should be B, and the other one should be A. A is the small one, B is the big one. Usually what's convenient to do is have the smaller sequence be 0. And the other sequence, bigger sequence, converges to 0. So if you can show that the terms of your in-between sequence are less than the bigger one, but always bigger than 0, then you get your limit is squeezed to 0. Usually, not usually, but often that's how you use a squeeze theorem. Your lower sequence is not really a sequence, well, it's a constant sequence of 0. So you can squeeze something between a convergent sequence and 0, that guarantees that it converges. All right, so that's one theorem that we can use. The next one is an absolute value theorem. And it can be convenient when we can use absolute values, because then we don't have to deal with sign changes. So we have a sequence A sub n. If the limit as n approaches infinity of the absolute value of each term is 0, that guarantees us that the original series also converges to 0. So if your series is converging, you think your series is converging to 0, but it's alternating in signs, you can just look at the absolute value and decide. So that can be helpful if you want to ignore the sign changes. So a couple of theorems that we can apply. All right, our main theorem for today. Questions so far? And especially the squeeze theorem, we kind of do this without even thinking about the fact that we're using the squeeze theorem. Kind of do it subconsciously. Main idea for today: monotonic and bounded sequences. So I'm going to say bounded and monotonic sequences. And if you do any kind of advanced calculus analysis, the idea of bounded and monotonic is one of the key ideas for convergence, one of the key ideas for a lot of things. All right, so we're going to make some definitions. We need to know what monotonic is. So we have a sequence, A sub n, is monotonic if its terms are non-increasing or non-decreasing. So what we mean by non-decreasing is we mean they go up only. They stay constant or go up. They never go down. That's what non-decreasing means, never go down. So I would write this as a sub 1 less than or equal to a sub 2 less than or equal to a sub 3 less than or equal to dot 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 less than or equal to a sub n less than or equal to dot dot dot. This is non-decreasing. The terms either continue to increase or they stay constant. They never go down. That's what non-decreasing means. And if I turn the inequality around, a sub 1 greater than or equal to a sub 2 greater than or equal to a sub 3 greater than or equal to dot 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 greater than or equal to a sub n greater than or equal to dot dot is non-increasing. So that means the terms only get smaller or stay constant. They never increase. So that's what we mean by monotonic. So they either always go down, always go up, or they can stay constant. But they never go the other direction. So that's why we call it monotonic. They always do the same thing. All right, so we good with that idea? All right, a bounded sequence. So another definition. And we're going to break this into several parts. A sub n is bounded above and these are intuitive ideas. If there is a real number m so that a sub n is less than or equal to m for all n. So all we're saying is there's some number that the terms of our sequence never get larger than. That's what we mean by bounded above. Pretty intuitive idea. And bounded below, we just turn that inequality around, basically. And we'll call this number n. So n is less than or equal to a sub n for all n. So there's some number that is smaller than every term of our sequence. It could be equal to the low term, but there's never a term of the sequence that's less than this number n. That's what we mean by bounded below. And then finally, a sub n is bounded if it is both bounded below and above. And I'm going to back up here really quickly, and I'm going to say m is the upper bound. There. And here I'm going to say n is the lower bound. So a sub n is bounded if it has an upper and a lower bound. So that's when we say our sequence is bounded, so if it has an upper and a lower bound. Now, the next part takes a little more work than we can do here, but it relies on this property, the property of the real numbers, that says they're complete, and the idea of a complete set means there's no spaces between, no gaps or spaces between the real numbers. There's always real number between another real number. So what that means is if we have some kind of bound on a sequence, then it has a least upper bound, the smallest one. And we can also say it has a greatest lower bound. So this relies on some of the properties of the real numbers. It gets kind of complicated. But what we're going to say is that bounded monotonic sequences converge. if our terms are sine x,
Yeah.
well, it's bounded. It's definitely bounded, but it's not monotonic
Oh.
because it increases and decreases. So it does sine x the sequence where it would be if our term of our sequence was sine n.
Monotonic means it has to only go in one
Only go in one direction.
Oh,
So
okay.
sine x increases and or decreases. So sine x or sine n for n equals 1, 2, da 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 would not converge because it's not monotonic. So this is our main idea from this section, is that bounded monotonic sequences converge. And it makes sense because if our sequence is bounded and it's increasing, well, that means eventually it can't get bigger than some number. So that least upper bound is going to be our limit. Same thing for a monotonically decreasing sequence. If it can't get smaller than some number, but it continues to decrease, well then it's got to converge to a limit. And the idea of bounded and monotonic really is at the base of all the stuff that we talk about with convergence. The absolute value theorem, the squeeze theorem, all of our limit rules have to do with really at the bottom of it, we're showing that sequence is bounded and monotonic. Now, sometimes the idea of bounded and monotonic is buried in the details of the other stuff, but that's really what we're doing. All right, so questions there. So what I want to do next is I want to come up with some examples of specific bounded monotonic sequence with specific requirements. So let's look at that. So let me grab this. It's going to go on a new page. Hi, Miss Cunningham. Here, you want to take one of these?
Yeah.
Because I'm trying to get rid of these that are on the side of mine.
Yeah. I do want one of those. Thank you.
Mm-hmm. Did I get that in the right place? Yes, I did. No? Oh, I was already there. All right, so we want to come up with a sequence that satisfies these conditions, and if we can't, then we have to explain why. So the first one, we want a monotonically increasing sequence that converges to 10.
Like
10 ln x. Well, ln x would be ln x increases,
How about then?
but it's not
converges
bounded.
to 1? What's the one that converges to 1? Is there one?
Yeah, so you're thinking along the right terms. Make it really easy. Okay, so Kira says a sub n equals 10. Is that monotonically increasing?
Yeah.
Yeah, because it can stay constant. Remember our inequality had an equal as well. So a sub n equals 10 is a monotonically increasing sequence that converges to 10. Yeah.
You have a sub n equals negative 1 over x plus 10.
A sub n, how about if I write it this way? 10 minus 1 over n.
Yeah.
How about that? So when n is 1, we're subtracting 1, so we're at 9. And then as n increases, we're subtracting a smaller and smaller number from 10. So our terms are going to increase monotonically. But the limit as n approaches infinity of 1 over n is 0. So both of those would work. This is the simpler one. This one, I think, is a little more interesting. Yeah, nice. How about a monotonically increasing bounded sequence that does not converge? What's that, Kara?
You can't do that because that definition of those terms
Right,
makes it convergence.
right. Bounded monotonic sequences converge. So I'm going to say not possible. in one of my classes for my master's degree, we did lots and lots of proofs. Pretty much everything we did was proofs. So the scariest one that I ever turned in was the problem would say prove this, prove that, and you just assumed that you were able to prove it. And the first time I did one, and I was like, wait, this is impossible. Then I was like, whoa, I better double check, because you can always, all of the problems you can prove that they're true. And that was like I was the most nervous turning in that homework assignment, because I said that the conjecture was false. That didn't happen very often. So that made me really nervous. So to say it's not,
Did you get it right?
yeah, I was correct. Yeah, I was excited. C, convergence that converges to 3/4. Yeah,
A sub n equals 3/4.
perfect.
Wow. Good job.
All right.
Good job, team.
Yeah. Can we come up with a more interesting one?
Minus n minus 1.
Okay, we could say a sub n equals 3/4 minus 1 over n. How about an even more interesting one?
1 minus
1 minus... How about... let me give you a hint. Think about horizontal asymptotes for rational functions.
3n plus 1 over 4n plus 2 is
Perfect. This would converge to 3/4. I like that one. I thought of this one when I thought of that one. But this is definitely the easiest one. And finally D. I'll go over here for D. An unbounded sequence that converges to 100. Right, what was that again, Kira?
If it's unbounded, how does it?
Right, if it's unbounded, does it converge?
I guess like it could be unbounded.
All right, the last thing I want to do here today is, before we do our little exploration, is some limits that occur frequently.
Limits that occur frequently.
The limit as n approaches infinity of the natural log of n over n equals 0. And as we write these down, can you think about how we would prove this? Can you think about how we would prove it directly? Using the squeeze theorem, for example.
ln x and then 0.
I'm going to say for n,
ln x
Well, why can't you just realize that n goes faster than ln?
Oh, wait.
all right, so here's one thing I want us to be careful of. What I'm going to ask for is a little more meat to our arguments than, well, the top grows faster than the bottom. So we've used that in the past. I'd like a little more kind of mathematical substance to our arguments.
For squeeze theorem, you use ln and 0 as your two functions.
I'm going to say for n greater than 1, the natural log of n is less than n.
That's the same the top goes faster than the bottom.
But you're showing,
That's just
but it's
expressed
showing
Right.
an
But
opposite.
you're showing.
Right.
So we can just write that, and that's basically
That's just the same thing.
So this is, so we'd say this is less than, ln n over n is less than n over n, less than 1. So we know the limit's less than 1. That's one way we could show that. All right, I'm going to erase this. That's just me thinking out loud. But that is a nice thing to remember. Okay, the next one, the limit as n approaches infinity of the nth root of n equals 1.
It's like some number to 1 over n, which 1 over n is
So like the square root is 2
some
is
number
1.
to 0.
No, but the thousandth root of 1,000 is pretty close to 1.
Yeah.
Yeah, because the root part of the
Right.
say it turns it into a fraction.
Right.
It's like n to 1 over n.
Right.
So
Oh,
it's easy 0.
Oh, so from infinity
It's
to
an
the power of
0,
0
which then is
1.
infinity form.
Oh,
So you have
but
to
it's
use
like
the
it's
hops.
for some
The hops. I call it the hops because it works. I don't remember what it's called.
So limit as n approaches infinity of x to the 1 over n is 1 for any x greater than 0.
Isn't that just the same thing as the previous one?
This is for, so here we're letting the part inside the root vary. Here we're just saying a large, very large root of any number as n approaches infinity.
So you could just express the first one as the second one because the x should still be very large. It still varies.
They're not quite the same. This one, the second one would lead to or the third one would lead to the second one. The limit as n approaches infinity of x to the n equals 0 for the absolute value of x less than 1. So if x is some kind of fraction between 0 and 1, this geometric series. And this next one is very important. The limit as n approaches infinity of n plus x over n to the n.
Wait, n or 1?
Is it 1 plus x to the n?
Yeah, 1 plus x over n is e to the x.
We proved this. I remember there was a.
Yeah, that was a physics.
There was a
thing.
proof.
We did that in physics.
Yeah, are we gonna learn how e equals mc squared?
No, but I'm hoping that we'll have time to do a lab where we can show to e to the I pi plus 1 equals 0.
Oh yeah, we're supposed to do that.
Today, I decided to do a different one today. That was more appropriate for what we were doing today. And finally, the limit as n approaches infinity of x to the n over n factorial is 0.
Yes.
And you might want to think about how you would demonstrate this, other than saying the bottom grows faster than the top.
Should we just break that into written saying the bottom grows faster than the top?
No, no. But how do you show that?
Ratio test.
We don't know the ratio. This is for a sequence. Ratio test is for a series.
Yes, the difference.
You can't take the derivative of n factorial.
Yeah,
Ratio test is for series. Sequence of partial sums.
So I can't use ratio test.
No. Ratio test is for series.
Okay.
So we can't just misuse it completely.
No, no, no. All right. Homework.
problems.
Jones converge.
Yeah, I think so. Yeah, I'm not 100% sure about. I'm trying to think. Is there an example that I can come up with